Yay!
Yay! Hey, let's do a quick example of how to apply Gauss's law. The more we're going to do these, the more Gauss's law might just sort of click for you. This is something that Gauss's law is something that usually students have a lot of trouble with. Because mathematically it's a little more sophisticated with surface integrals and all this stuff. But the core concept of it is something that when you see it more and more often, it just sort of makes more sense, right? You sort of intuitively understand it a little bit better. So let's start with examples like that. Okay, here, what I've got is an electric field. I just gave it 500, a strength of magnitude of 500 newtons per coulomb. It's just traveling in the x direction, and it's totally uniform. Right, so everywhere it's the same value, and it encounters this hemisphere. So the electric field is going into this flat area, right? It's going in there, and then it's coming out of the curved area. What I want to know is what is the flux through the hemisphere, and what I mean by that is the part on the right. Let me make that more clear. On the right. So what is the electric field flux through that curved surface? That's what I want to know. Okay, so what we need to do is write down what is flux? What is the electric flux? Well, electric flux is, I mean, there's a really fast way to do this, but let me step through it. The electric flux is, it's just sort of defined as the dot product of the electric field through some area, right? The problem is that through the hemisphere on the right, through that curved surface, the problem is, what is that dot product, right? That's going to be EA cosine theta, where theta is the angle between the electric field and the direction of the surface, the orientation of the surface, that normal vector to the surface. Well, the problem is, over here, look, I've got a little patch of surface right there, and the little area vector from that patch of surface, the normal to that little patch, is pointing at some angle right there, right? So there's my theta here. Well, at some other point, like down here, I got some dA. Now my normal is pointed down there, right? And I have got some, other angle down there. So the point is that all over that surface, I have a whole bunch of different angles that E makes with the surface normals. So what I'm going to have to do to get the total flux is I'm going to have to integrate, I'm going to have to integrate E dot, those little surface normals, all over that surface, all over that hemisphere. That looks difficult because I'm going to have to integrate over the surface of the sphere, and if you remember from what we've done before, that's not a totally simple thing to do. Okay, Gauss's law to the rescue, because this having to do this might make you a little sad. So what we're going to do instead is use Gauss's law, and Gauss's law says in integral form, Gauss's law. It says that if I integrate the flux, if I add up the flux through a closed surface, that little circle there means a closed surface. If I add all this stuff up, E dot dA, over an entire closed surface, what's going to happen is that's going to be equal to the amount of charge in the surface, enclosed by the surface, divided by some number. Turns out to be epsilon naught. So let's say here there is no charge enclosed, just an empty volume, just an empty surface. So that means that the total amount of electric flux is going to be zero, right? So here's how we can use Gauss's law as a shortcut. Is there's no way I want to integrate over that closed surface on the right, the hemisphere surface to the right. But look what happens on the left. Where the electric field is going in to that flat disk on the left, here's my, just let me use a different color just so it's easy to see. Here's my surface normal, A, right? That's easy because E and A, there's just the one angle. It's just, 180 degrees, right? E and A are oppositely directed. So determining the flux through that thing is going to be really simple. So through the disk, E dot A, the flux through the disk, E dot A is just going to be, let's see, I give it a strength of what, 500. Look at the dot product. That's EA cosine theta, right? Well, A is pointing to the left, E is pointing to the right, so the theta is 180 degrees, so I pick up a negative sign, so I'm going to have negative times, what's the area of that disk? Pi r squared is just the area of the disk. Oh, I didn't write it down, I guess. Let's say that this is, I don't know, 0.2 meters. The radius is 0.2 meters, so let's see, it's going to be pi r squared. So it's going to be pi times 0.2 squared. And so when I did that, what did I get? 63 minus 63, whatever the units are, newtons per coulomb times meter squared. Okay, so there's the flux. That's the flux coming in. It's negative because it's going into the surface. That's how it's defined. And now we use Gauss's law. If I know the flux going in, then immediately I know the flux going out. If there's no charge in there, then whatever goes in has to come out because the total is 0, right? So that means the flux through the hemisphere equals plus 63 because they have to add to 0. So that's an example of turning a hard problem into an easy problem. I know how to get the flux going in. That's easy. And so that tells me what the flux going out has to be, even though that's a really hard calculation. Okay, so that's one example of using Gauss's law as a shortcut, which honestly we do a lot in physics and laws like it. But also it kind of increases your intuition about how Gauss's law is supposed to work. And just the idea that you can tell how much charge is enclosed by the surface by looking at how much flux is coming out of the surface is what Gauss's law is all about. That's the core idea. And so that's what we'll do some more examples of.